Welcome everyone to a second session with Ángel González Prieto. This time we're going to talk about a paper called On Character Varieties of Singular Manifolds. It's related to the previous interview that we've discussed already, so if you haven't seen that, it could be a good idea to check it out. But without further ado, we'll get started with this one. Would you mind just, on a very high level, give an overview of what this paper is, and if there is a connection as well to the paper that we already discussed last time?
Of course, I will be delighted to. So the idea of this paper is when you have a manifold, and with a manifold I'm meaning a space in which there is interesting geometry. To understand this space, one thing that you can do is to associate another space that is more algebraic in some sense. It's a space that can be understood in a better way through more analytic techniques. So the space that we want to associate in this paper is something called the representation variety. And essentially, the idea of the representation variety is that you have your manifold, and on top of your manifold, you want to understand the ways you can represent your manifold in a certain vector space. In a very, I'm very sloppy here, but this is kind of the idea, to understand how can I represent my manifold in a different manifold, in a different vector space. And this is called the representation variety. This representation variety is extremely important in geometry in general, because it turns out to be isomorphic, equivalent to other important spaces, like, for instance, solutions to PDEs, partial differential equations associated to particle physics on the manifold, and other different geometric important problems, classification problems. So understanding the geometry of this representation variety attached to this original space is an important issue. And the thing that we do in this paper...
Yes. So you're saying understanding the geometry of this representation variety. So you talk about it as if the representation variety is some form of space itself, or at least some geometric object, let's say. The way I conceived it is you articulated it originally as if it was, or I understood it as if it was more like a transition of bases, let's say, or transition of spaces. So you're in this one space and you want to express it in another one. But then we're talking about the representation variety itself as if it is a geometric object of sorts. Could you highlight that point and maybe clarify if I'm misunderstanding something, or if you mean if that indeed is how to think about it?
That's the perfect way to understand this. So I have my space, and I want to represent my space in a different space, and the ways I can represent my space itself form a new space. And this new space is called the representation variety. So it's another space attached geometrically to your original one. This idea of attaching a space to another space to understand it in a better way has been used, for instance, to understand the geometry of four manifolds, the varieties spaces of dimension 4. And it turns out that dimension 4 is a very complicated dimension geometrically. Things that doesn't happen in other dimensions happen in dimension 4. And to understand,
do you have an example of that? Like an example of what's specific about dimension 4 that...
Wow, I can tell you plenty of crazy examples. One of the important examples one of the important examples is the Euclidean space. You consider the Euclidean space Rn, and the Euclidean space turns out to be unique in a sense in dimensions different than 4. But in dimension 4 there are many non-equivalent Euclidean spaces, and there are actually infinitely many different Euclidean spaces in R4, in the Euclidean space of dimension 4. So this is a special feature of dimension 4 that doesn't happen in other dimensions. And it's because typically the way we try to understand this is because in dimension greater than 4, you have enough room to do movements. So if you want to convert something into another thing, you have enough room to move it and to change it to the guide that you want to study. And in dimension less than 4, there is not enough room to do crazy things. If you want to twist something a lot, there is not enough room to twist it. So even though you don't have enough room to solve the difficulties, you don't have also enough room to create these difficulties. And dimension 4 is a special point in which you have not enough room to solve it, but you have enough room to create them. So crazy things happen. And this is actually something philosophically problematic, because dimension 4 is the dimension of space-time. So it's something like the university is trying, the universe is trying to cheat us in some sense. Because
is it generally more problematic that we have to deal with dimension 4 in the context of trying to represent the universe, or is it sort of like, is there a clear benefit or drawback of having this these special features in dimension 4 from the perspective of making sense of the mathematics?
That's a very, very important question. I will say that is both a blessing and a curse. And let me explain this. It's a blessing because it provides a lot of interesting examples that you wouldn't get otherwise, and also allows you to have different phenomena that may happen and that you may not happen if this was not the case. So in this sense, it's a blessing because it's something good that you have enough flexibility, but it's also bad in the sense that it's more difficult to understand. But mathematicians like challenges. So in this setting, even though it's bad, it's good for us because it's good to understand.
It gives you more jobs, no?
Exactly. More joy.
Anyway, I'll let you get back to the explanation. Thanks for the example.
Sure. So this is the idea. For instance, if you want to understand this dimension 4, you want to understand this Euclidean space that has different non-equivalent instances, the way you understand this is by attaching a different space that is complicated, but is more treatable in a sense. You can treat it with more analytic techniques. And one of the spaces that you can associate is precisely this representation variety. And the representation variety is a new space itself. So it's a new space attached on top of your original space. And understanding the geometry of this new space is also a challenge, but probably is more feasible than understanding the original geometry. That's kind of the idea. It has actually the way I would like to say is that the representation variety has more structure than the original space, even though it might be complicated, is better behaved. It has more structure, and since you have more structure, you have more techniques, more tools to understand this space.
In terms of dimensionality, are they the same? Like the representation variety?
No. The representation variety has a much bigger dimension, and that is also good because if you remember, from dimension 5 on, things are easier. So no. The dimension is actually not related with the original dimension. Let me say this in a different way. You have a surface, and depending on the surface in which you are, the dimension of the space that you are attaching is different, even though you are attaching this to a surface, dimension 2 space.
Okay, so it's dependent on the structure of the surface itself, not so much the dimensionality.
Exactly. And that's actually one of the important invariants. If you want to distinguish two surfaces, you attach this space, you measure the dimension of these spaces. If the dimension of these spaces is different, then the original spaces are different.
Okay, so is the representation variety invariant as well? Or, well, you can maybe calculate invariance from it?
The representation variety is invariant itself, in the sense that if you have two spaces that are isomorphic, their representation varieties are going to be isomorphic. So the representation variety as a space, it's an invariant, but a space itself is difficult to understand. So the way you understand this space is through its invariance. So you say, okay, for instance, its dimension. So instead of understanding the representation variety as a whole, I understand the dimension of the representation variety. That's an invariant.
Mm-hmm. Okay, understood. How do they now tie back to the paper and just the context that we were discussing before?
The idea of this paper is that we develop these topological quantum field theory techniques to understand how these representation varieties change when we glue different spaces. So for instance, suppose that you have like a tube, and on top of this tube you have a representation variety, and this tube is not a smooth tube in the sense that this tube has a hole on it. There is a hole on it. So I have this representation variety on my tube, and I want to attach this tube to a different tube, like a pipe. You have a pipe and you attach this pipe to a different pipe. So something is going to happen to your representation variety. You have the representation variety of the original tube, you have your representation variety of the second tube, and you want to understand what is going on when you glue them together. And what happens is that the geometry of the glued representation variety is governed by a topological quantum field theory. There is a topological quantum field theory understanding the way this combined representation variety arises. And we exploit this idea in this paper to say, because the key point is the following. Every surface with no boundary, so a surface that has no end, is always a combination of these tubes. Let me say this in a different way. The most simple surface that you can have is the sphere. The sphere has 0 holes. Then you have the torus. The torus is a donut, is something like this, and there is a hole in the middle. Then you may have the 2 genus torus, which is a torus, so it's a donut, but with 2 holes, or 3 holes, 4 holes, and so on and so forth. And it turns out that these are all the possible surfaces that you may have. And these surfaces can be constructed through a general pattern. And the pattern is take a disk like this, take a tube with a hole in the middle, glue this tube here, and glue this tube as many times as you want. So if you want 90 holes, then you have to glue this tube 90 times, and then you glue back another disk. So you get your disk, as many holes as you want, and the final disk to close the boundary. So if you understand the way you can glue these spaces through this gluing procedure, then you can understand them for all the surfaces at once. Only with one computation, just understanding how they glue, you are able to compute them for all the surfaces. And this is something very striking in a sense, because typically you need to do a particular study for genus 1 hole, genus 2 holes, genus 3, and so on and so forth. And here we said no, you can do it with only one calculation.
Okay. I think we touched upon the same kind of concept in the last interview as well. So given that we have the objective sort of clear for the paper now, maybe we can focus on some of the constituents that are in this abstract as well. So I think the first keyword, let's say, that we could paint some more picture around is the lax monoidal topological quantum field theory. We briefly touched on this in the last session, and I think you gave an explanation along the lines that lax monoidal is sort of a less stringent criteria than being monoidal, and I think it has to do with dimensionality, that the lax monoidal one can be infinitely dimensional, if you will. Is that the definition of this, or how come, first of all, what is the difference, and then how come we're going for a lax monoidal in this case and not something more stringent, if it really is in that way that I described?
That's perfect. You nailed it. So the idea is precisely that lax monoidal here means that there is a kind of entanglement, of quantum entanglement, beyond the classical entanglement, in the sense that what you assign to a disjoint union is not the product of the spaces that you will get, but something bigger. And this is related to the fact that the quantization that you get is infinite dimensional. This is exactly the case that we have here. actually, the chronological appearance of these papers were, this was a paper that we published before the one we were discussing the other day. And the point is that in this paper, we constructed this topological quantum field theory that is Lax monoidal. And we thought, okay, we have this Lax monoidality feature. We will want to get rid of it because it's not very beautiful. It gets infinite dimensional things and you don't like them. Let's try to get rid of it. And then I realized we can't, because there is a fact that says this paper is sharp in a sense. The construction of this Lax monoidal TQFT is the best that you can do. You cannot do it without the Lax monoidal hypothesis. And it's because in the other paper, I prove no. There are some constraints in the problem that you want to understand that prevents you to have a monoidal TQFT.
Okay, understood. So then, if we stride along sort of the abstract here, this topological quantum field theory computes virtual classes in the well, I don't even know how to pronounce the name here, so maybe you can do that for me.
Grothendieck.
Okay, and this is a ring of algebraic varieties. Can we paint a bit of a picture of what this actually means now? This ring of algebraic varieties, what does it
This
represent?
is a very technical word, so it's very good that you asked this question. So, when you want to understand a space, an algebraic variety, that is the technical name of the spaces that arises, is the technical name of what is a representation variety. These spaces, is natural to do cut and paste. And let me explain this. Maybe you have your space, it's very complicated, and you want to say, okay, this space is super complicated, but in the middle of this space, I want to remove a line. And you cut a line and you get it out, and then you get a new space that is your original space minus a line. And maybe your original space is now easier, in the sense that now is equivalent to something that you already know, like an Euclidean space. Maybe it happens that your original space is not Euclidean space. It's only the Euclidean space after removing a line. So you can say my space is the Euclidean space plus a line, meaning that I can decompose my space into simpler pieces. And the simpler pieces is Euclidean space and a line. And that's the kind of things that you can do in the Grothendieck ring. In the Grothendieck ring, what you do is you give a description of your space, but up to cut and paste, up to removing things, putting things back, and this stuff. The typical example that you may have in mind is the sphere. If you consider the two-dimensional sphere, the two-dimensional sphere is a complicated space, but if you remove a point from the sphere, then what you get is simple, because if you remove a point, then you can bend the sphere to a plane. Actually, this is called the stereographic projection. It's the kind of projection that you get in maps, in geographical maps. You get a projection from the North Pole, and then you get a plane map of your sphere, except a point, the North Pole. So you may say the sphere is actually a plane plus a point, the point at infinity. And this is the kind of description that you will give in the Grothendieck ring of algebraic varieties. Instead of saying sphere, which is a complicated space, you say plane plus point, which is a much simpler space. And it turns out that this description up to cut and paste is an invariant. And it's typically an invariant that can be given as a polynomial. And I can explain this very easily. So I'm saying I have a plane plus a point. Let's say that the plane, let's assign to the plane a variable, a name. Let's call it q squared. Squared because it's dimension 2. So we have said that the sphere is 1, because I have a point, plus q squared, because it's the affine space, the Euclidean space of dimension 2. If you have something that is more complicated, like a point plus a plane plus a 4-dimensional space plus a 6-dimensional space, then you could get 1 plus q squared plus q raised to 4 plus q raised to 6, because you have this decomposition. But at the end of the day, you get a polynomial. And this polynomial tells you what is the decomposition. That's the idea. This TQFT, this lax monoidal TQFT that allows us to understand the way you glue things, what is computing, the invariant that is computing is precisely this polynomial attached to the representation variety, which is how is this representation variety up to cut and paste.
Okay. Can any surface be mapped onto this ring of algebraic varieties? Or are there, like, what's the appropriate way of thinking about this? Is it, let's say, something that you can apply to any given surface whatsoever, and it just is sort of you apply a looser condition on how to specify the surface itself? Or is it something, like, are there sets of criteria that you need to fulfill in order to exist or to be part of this ring, let's say?
No. Every space is part of this ring. Every space is part of this ring. The interesting point is that even though you are part of this ring, you want to understand, you want to write this element in a simpler way. So in particular, a sphere is an element of the Grothendieck of algebraic varieties, but it's a new name, it's a new variable. But it turns out that this new variable is not actually a new variable, because it can be written in terms of the previous one. Is
Okay,
one
so it's the other way around, no? Like that every space is a subset of this ring?
Exactly. It's an element. Actually, it's an element. It's an element of this ring, but it's an element, it's a new name, and I want to write this guy in terms of simpler guys, typically in terms of Euclidean spaces, in such a way that I get a polynomial. So there are no conditions at all. Every algebraic variety is part of the Grothendieck ring of algebraic varieties. A ring is a place in which you can multiply and sum. This ring is super complicated. I mean, it has all the pathologies that you study in commutative algebra appears in this ring. So this ring is very complicated. It has no good properties at all, but and it's very complicated because it contains everything. Everything is inside the Grothendieck ring of algebraic varieties, and they have very crazy relations. So understanding what is the virtual class, what is the image of this variety in this Grothendieck ring is crucial, because it's a very, very important information. Is how can I decompose my space into Euclidean spaces? And having this decomposition is a miracle.
Okay. Are there sets of spaces where that is very well mapped out, where you have this relationship, or how do you go about finding that in general? Like, if you don't have a specific problem, there's no recipe, I take it, for trying to figure that out, but you really need to approach every problem individually for that.
So that's a very good question. In general, if you give me a random algebraic variety, I have no clue how to decompose it into simple pieces. So this is a very complicated problem. In particular, there are open problems like I have this variety, I have this variety. I don't know if in this ring they are the same or not, in the sense that I don't know if, okay, they are different on the nose, but I don't know if there is a super clever way of decomposing them into simpler pieces in such a way that each piece is different. So it's like I have a Lego puzzle, and the Lego puzzle, the original pieces are the same, but I put them together in different ways. But the Lego pieces were the same or not. And these are open problems. So being able to do this for representation variety is a miracle, in a sense.
Okay. So the mapping is difficult to figure out. Is it unique in the sense that you have two surfaces that are isomorphic in this space, and then you try to map them onto this ring, and then the decompositions would be isomorphic themselves, or are we is there something else that holds? Like, would you know, if you know how to map them, are they unique in the sense that you would know that you two things that you see mapped to this ring would be isomorphic, and you could extract from that the original ones are also isomorphic?
So the answer is if there are two spaces that are isomorphic, their image in this Grothendieck ring of algebraic varieties is the same. If the image in the Grothendieck ring of algebraic varieties is the same, then they might not be isomorphic on the nose. and there are examples of that. So,
Okay,
so
so
the
it's not
map
bijective.
is not bijective at all, and that's important. That's interesting
Yeah.
because, I mean, if it was bijective, then it's exactly the same information. The point
Mhm.
here is that you say, okay, now I am understanding different spaces that are different spaces, but in a sense are kind of similar, up to cut and
Mhm.
paste. And I can give you
Mhm.
an example actually. Consider a curve like this, and then
Mhm.
you like a cusp, and
Yeah.
this cusp is wild in a sense that it's not smooth, it's not a smooth function in a sense, but now I remove the cusp, I remove this point. When I
Mhm.
remove this point, what I get is a smooth space because I have
Mhm.
removed precisely the peak. And this space in which I have removed the point is actually isomorphic to a line minus the point in which I have
Mhm.
removed the point. So it's a line minus a point. And then this point I can put it back because I am allowed to do cut and paste.
Mhm.
So in the Grothendieck ring of algebraic varieties, this curve and the line are the same, even though
Mhm.
they are not isomorphic. This one is singular, this one is smooth. So, and it's because both of them were created using the same Lego pieces, a line
Mhm.
minus a point and a point. But in
Well,
the
I guess it depends on how much information you include in the Lego pieces, right? Like
exact
we're splitting this up now, and we're saying presumably that the only thing that matters is, let's say, the parts of the line itself in this case that are included, but we don't consider, let's say, the derivatives in each point. How much information do we actually care about in this ring? Like, do we discard any information that is not, let's say, the function value if you describe this surface or manifold or line as a function?
so the point would be like um when I'm saying algebraic variety means something very specific. Means a space that is given as zeros of a polynomial. So I have a polynomial in several variables, and I look at the zeros of this polynomial, the places in which this polynomial vanishes.
Mm-hmm.
Uh, when I'm saying I consider up to cut and paste, is I'm considering the zeros of this polynomial, and I'm allowed to remove some zeros of the polynomial. But what I get now is again a polynomial equal to 0 minus that these cases are not allowed. So this is the
Mm-hmm.
kind of information that you are allowed to get rid of. Like
Mm-hmm.
saying you still get the polynomial, you still remember that there was a polynomial, but the now you are allowed to remove some points in the zero set of this polynomial. So in a sense, you are getting all the information that's true, but in a polynomial way.
Mm-hmm. Okay. Okay. Cool. So we have this construction now, and the construction is valid for any algebraic group G in any dimension and also in the parabolic setting. What do we mean by the parabolic setting here? Why does that matter, and how does it relate to what we talked about?
That's a very good point. So the point is, I'm understanding representation varieties. Representation varieties are varieties, spaces, algebraic varieties associated to a given surface. But parabolic means that in this surface, I am allowed to remove points. So instead of looking only at spheres or torus or two genus torus and so on, I'm allowed also to look at a torus minus 5 points. And removing these 5 points is interesting from a physical point of view because as I was mentioning, uh, these representation varieties are equivalent to solutions of a certain PDE arising in particle physics called Jam-Mills equations. And if you only consider surfaces with no removed points, with no parabolic structure, then the solutions that you get are very mild. But if you are allowed to remove these points and to get some poles, the solutions may develop some singularities at these points, and you get something more complicated. That is called the parabolic structure. So parabolic in this setting means that I am not only considering surfaces, I'm considering surfaces in which I am allowed to remove as many points as I want.
Hmm. Okay, so it's kind of a robustness assurance, let's say, for the approach.
Yeah,
Like
kind
this
of.
statement that it's also valid for, or that it's also valid in the parabolic setting.
Exactly. So it's like it's valid in the parabolic setting. It's also valid in the non-parabolic setting. We are developing a TQFT that works both for surfaces with no remove points, but also for surfaces with remove points.
Hmm. Okay, cool. The next sentence then is, in particular, this TQFT allows us to compute the virtual classes of representation varieties over complex singular planar curves. In addition, in the case G equals SL2 of K, the virtual class of the associated character variety over a nodal closure orientable surface is computed both in the non-parabolic and parabolic scenarios. What is this, the case G equals SL2 of K? What do we get from that, or what is that?
That's a very good question. So I was mentioning that these representation varieties give you the ways in which you can represent your space in as a given vector space. But you have to fix the dimension of this vector space. And when I'm saying G equal to SL2K, what I'm saying at the end of the day is that I'm saying that I want to represent in a two-dimensional vector space. And
Mhm.
the way you have to understand this is a two-dimensional vector space is because SL2 SL2K is the space of 2 times 2 matrices with entries in the field K, so with entries in a given field of determinant 1. So what I'm saying is that I'm considering 2 times 2 matrices, and I'm considering the ways in which I can understand my space as these 2 times 2 matrices. And at the end of the day, this is the way in which you can understand a 2 times 2 matrix. The way you have to think about a 2 as for a 2 times 2 matrix is as a linear map on the two-dimensional Euclidean space. So I'm representing my points in the two-dimensional Euclidean space. This is what G equal to SL2K means in a super particular technical meaning.
What's the reason for considering this in particular?
Because I can do the calculations for this choice and not for other choices.
Okay.
So let me explain this. If you
Mhm.
want to represent in dimension 1, in a one-dimensional vector space, things are very, very easy. You can do it
Mhm.
very easily, and actually you can do it in general and any manifold, not only surfaces and this stuff. So one-dimensional spaces is very easy. It's the so-called abelian case, because in some
Mhm.
sense the things commute. In the two-dimensional setting, when you want to represent into a two-dimensional vector space, it turns out that the things are much more complicated because there is no abelianity, there is no commuting things, and it's a complicated, very complicated setting, but doable enough to do the calculations. If
Mhm.
you go to a three-dimensional space, four-dimensional space, seven-dimensional space, things are much crazier. But
Mhm.
even though it's a setting in which things are doable, they are also interesting in the sense
Mhm.
that there is a parallelism between these two and the two in the surface. Like I'm representing in a vector space that has the same dimension as my original surface, and interesting features arises in this case. In
Mhm.
some philosophical sense, the SL2 case, the case of dimension 2, contains all the possible features that can arise in a higher dimension. But at the end of the day, the answer is because I can do it in this dimension, and in dimension 3 is much more challenging.
Okay. Is there anything intelligible we could say in dimension three, or is that simply like, do we lose, let's say, all ability to draw any intelligent inferences in that dimension?
So what happens in dimension 3 is the following. In dimension 2, the kind of pieces that can arise are simpler.
Mhm.
I think they can arise 6 different pieces. You need to understand 6 different Lego pieces to decompose your variety. In dimension 3, you need much more pieces, like of the order of 30 or something like that. So the number of pieces grows exponentially, and the number of calculations that you need to do grows exponentially. So it's true that if somebody will tell me, if you do the calculation for SL3, I will give you $1 million. Then I will lock down, do the calculation for 6 months, and I can do it. But it's much, much more complicated in the sense that there are much, much more pieces. At the end of the day, what happens is that this topological quantum field theory, at the end of the day, is a matrix, and it's a matrix number of pieces times number of pieces. Since this is a 6-dimensional thing, it's 6 times 6, essentially. But in the case of something that is 3-dimensional or 4-dimensional, it will be a matrix 30 times 30. And so I will have to compute 30 times 30 entries of the matrix.
How positive is the prospect of being able to use computational techniques to help with these things? Is there any sort of overlap between emerging computational techniques and solving these kind of very algebraically tied problems that we're seeing in academia?
That's a very, very interesting question. The answer will be a lot. My hope is that in the future we will have computational techniques to address these problems. Let me say something. I know for a different case, but also very difficult. I have some collaborators, Jess Vogel and Marto Havlicek from the University of Leiden, that they took these ideas for SL2 and they managed to apply for much higher dimensional spaces using the computer, because they realized that even though there are much, much more pieces, they can be treated kind of the same, with the same algorithm. So they developed an algorithm to treat these guys, and they managed to fill out every possible entry of the matrix using these computational techniques. So yes, you can do it. Also, I have a brilliant PhD student, Alejandro Calleja, and he's also working in a different setting. It's not the setting of surfaces, it's the setting of 3-dimensional manifolds, but he's actually working in extending these calculations for dimension as higher as needed. So in particular, in a different paper, we managed to do these calculations for dimension 3. So underlying dimension 3, our representation varieties over 3 manifolds, up to dimension representing in dimension 2, 3, and 4. 2 and 3 were known previously, and 4 was our contribution. And for dimension 4, this was a joint paper with Vicente Muñoz, and in this paper, we essentially develop an algorithm to do the calculation. We say, okay, there is like 300 possible pieces, but all the pieces can be treated the same. We implemented this algorithm, we execute it for a day, and then you get the right answer. So you can do it. And my PhD student is trying to extend this to higher dimension, as big as needed.
Okay, some of your other work is also related to machine learning at the moment. Is there any kind of connection between the techniques developed there and something that could be leveraged for this? Like, do you see any kind of overlap between those two fields, or are they, for the moment being at least, strictly separate?
I mean, there are very interesting contact points. So let me explain this in a different way. So far, the computational techniques that we have used are classic, in the sense that we created an algorithm, we execute the algorithm, we get that result. No training, no testing, just you have to do a lot of calculations by hand that are not doable by hand. But it's true that the pattern is kind of similar in all the possible calculations. So it will be very, very interesting to try to say, okay, I want to train a machine learning algorithm to understand, okay, there are 300 pieces, but all the same have the same pattern. So I want to develop by myself the algorithm that I need to execute to compute them. Because I have seen enough examples of this calculation. Like I give you 20 calculations of these pieces, and the machine learning algorithm is able to say, okay, I have understood what is the pattern. You don't need to give me the algorithm. I will create the algorithm for you, and I will execute it. Yes, this is something very, very, very interesting. This has also been studied because other invariants, not exactly the class in the Grothendieck ring of algebraic varieties, but other invariants are also very complicated, and there are some physical theories that predict some symmetries in this invariant. They say, okay, this invariant and this invariant has to be symmetric in a sense, but this is a completely physical argument. Like the universe, we think that the universe is works in this way, and since we think this should be the case. But this is not a mathematical proof. There is no mathematical proof of this statement. This statement is called mirror symmetry, and it's a very complicated topic. But even though we don't have a proper proof of this statement, what we know is that you can train a machine learning algorithm to predict the mirror of your space. So you have a space, and the mirror symmetry problem is to construct another space, another algebraic variety that has mirror properties. Even though we know how to do it in 1,000 examples, we don't know how to do it in general. But it turns out that you can train a machine learning algorithm with 1,000 examples that you know, and the machine learning algorithm is able to do it with a 99.9% of accuracy. So even though we don't know the pattern, the machine learning algorithm knows the pattern.
Right. Yeah, I guess a lot of that is on the horizon as well, so that's quite interesting. Just bringing this back to the paper, because we really need to close now as well.
Yeah.
Would you like to summarize just any findings that I didn't touch upon, let's say in our quick walkthrough of the abstract here? Is there anything you would like to conclude with before we close?
Yeah, sure. So I think that something interesting to have in mind of this paper is that we have this representation variety, complicated spaces attached to a given space, but maybe not so complicated as the original space. To these varieties, we want to understand the Grothendieck ring of algebraic varieties. We want to understand its image in this Grothendieck ring, what is called the virtual class, and we would like to understand it as simple as possible. And the magical statement of this theorem is that through this topological quantum field theory, you can understand this image as a polynomial, and the polynomial is actually given in the paper. If you scroll down a bit, that polynomial, which is a polynomial in Q, with this other part. So it's a very, very complicated polynomial. It's a polynomial in the variable Q, because it's the typical name of this variable in this setting. But even though it's a very complicated polynomial, it's an explicit polynomial. It says that your space, your representation variety is, and you can read this, like, for instance, you have this Q minus 1 raised to whatever. This means a plane minus a point, as many times as needed. 2G plus R minus 1. So this gives you a super precise decomposition into simpler Lego pieces. And I wanted to show you this formula because I wanted to explain to you that explicit is not something like, I think that is explicit because I know about the topic. It's explicit because this is the formula. These are the pieces.
Right. Okay, awesome. Thank you very much for the overview. Thank you very much for taking the time to do the interview. And yeah, all the best.
Thank you. Thank you very much. Thank you very much. Have a good day.